Imagine processing a document the size of a novel or a million lines of code for an AI. 6 Sol, that single operation could cost you $5. But with DeepSeek V4 Flash, that same task drops to just 14 cents. That's not just a small discount, it's a seismic shift in the economics of artificial intelligence. For anyone building with large language models, the cost of their context window is one of the most critical bottlenecks. The context window is essentially how much information the AI can hold in its mind at one time, the length of the prompt you give it, plus the length of its response. Until recently, expanding that window meant exponentially higher costs, limiting what AI could do. A $5 charge for processing a million tokens, which is roughly 2,000 pages of text or a massive software codebase, quickly adds up to hundreds or thousands of dollars for complex tasks. This makes many ambitious AI applications simply too expensive to run at scale. So, how did DeepSeek slash that price by over 97%? The answer lies deep within how these models pay attention, and how DeepSeek rewrote the rules with 2 clever architectural changes. At the heart of every modern large language model is a mechanism called attention. It's how the AI weighs the importance of different words in your input when generating its output. Think of it like a student reading a complex textbook. To understand one sentence, they might need to refer back to another sentence on a previous page, or even glance ahead. The attention mechanism does this for every single word, or token, in its context window. Every token has to look at and evaluate its relationship with every other token. This is incredibly powerful for understanding nuances and long-range dependencies in text, but it comes with a massive computational cost. If your context window doubles, the amount of calculations required for attention doesn't just double, it quadruples. If it triples, the calculations multiply by 9. This is what engineers call quadratic scaling, and it's the invisible wall limiting how large and how affordable AI context windows can get. 6 Sol. Imagine a million tokens in the AI's mind. Each of those million tokens needs to consider its relationship with the other 999,999 tokens. That's nearly a trillion individual connections to calculate. These calculations don't just consume vast amounts of processing power on specialized chips called GPUs. They also demand enormous amounts of memory. Holding all those connections in active memory, even for a brief moment, is a significant engineering challenge and a constant drain on resources. The energy consumed, the heat generated, the sheer volume of data moving back and forth across the chip, it all translates directly into high operational costs. For companies like large software development firms or legal tech platforms, routinely analyzing vast codebases or hundreds of pages of legal discovery, a $5 charge per million tokens quickly adds up. Processing just 100 such documents could cost $500, and for operations scaling to thousands or tens of thousands of documents daily, compute bills can soar into the tens of thousands or even millions of dollars every month. This makes many ambitious AI applications simply too expensive to run at scale, acting as a hard ceiling on innovation. But what if an AI didn't need to look at every single token in relation to every other token? What if, like a human reader, it could be more selective? This is the core idea behind sparse attention. Instead of a dense all-to-all connection network, sparse attention aims to create a more efficient, selective network. Think of it like a social network. In a dense network, everyone is friends with everyone else, a huge number of connections. In a sparse network, people only connect with their closest friends, or perhaps friends of friends, or a few key influencers. The overall information flow can still be very rich, but the number of direct connections is dramatically reduced. For AI, this means fewer calculations, less memory, and ultimately lower costs. The challenge, of course, is deciding which connections are truly important and which can be safely ignored without sacrificing the model's understanding and performance. Many research efforts have explored sparse attention, often by trying to approximate the full attention mechanism. But DeepSeek took a different approach, building native sparse attention right into the model's fundamental architecture. Instead of retrofitting sparsity onto an existing dense design, they made it a native feature from the ground up, integrating it deeply into the training process itself. Their system focuses on 2 key types of connections. First, a local window attention. Each token primarily focuses on a small group of tokens immediately surrounding it. This is like a reader focusing intensely on the words in a single sentence or paragraph to grasp its immediate meaning. This captures immediate context very efficiently, much like how adjacent words are often the most relevant to each other. Second, a global connection mechanism. Certain tokens, perhaps those deemed more important due to their position or content, or those at regular intervals, maintain connections across the entire context window. This is like a reader occasionally scanning chapter titles, the introduction, or the conclusion of a book to keep the overarching narrative in mind. This allows the model to bridge long distances and grasp overarching themes, even if it's not exhaustively connecting every single token to every other. By carefully designing these native sparse connections, DeepSeek dramatically reduces the quadratic scaling problem, turning billions of potential calculations into mere millions without losing crucial context. However, simply reducing the number of connections isn't enough. If an AI is only paying attention to a select few tokens, how does it quickly find those important tokens? Imagine a traditional library where every book is cross-referenced with every other book. That's dense attention. Now imagine a library where books are only connected to a few others, a sparse network. If you want to find a specific piece of information, you can't just randomly browse. You need an incredibly efficient index, a system that tells you exactly where to look for the relevant connections. Without such a system, the AI would spend more time searching for the right sparse connections than it saves by having fewer of them. This indexing problem becomes particularly acute with massive context windows, where the sheer volume of tokens makes any inefficient search operation prohibitively slow and expensive. This is where DeepSeek's second innovation, the Lightning Indexer architecture, comes into play. The Lightning Indexer acts like a hyper-efficient librarian for the AI's sparse connections. It's not just a passive list, it's an active, optimized system designed to rapidly identify and retrieve the most relevant tokens for any given calculation. Think of it as a specialized hardware and software layer that pre-processes the input, creating a highly organized, dynamic map of where important information resides within the vast context window. This map isn't static. It constantly updates as the AI processes information, prioritizing the most likely relevant connections for the current task. When the native sparse attention mechanism needs to make a connection, perhaps looking for a global theme or a specific piece of information from a distant part of the context, the Lightning Indexer doesn't just provide a list of possibilities. It points the attention mechanism directly to the most promising candidates, almost instantly, bypassing the need to sift through irrelevant data. This significantly reduces the overhead associated with sparse attention, ensuring that the computational savings are realized in practice. It transforms a potentially slow, fragmented system into a fluid and incredibly fast one, allowing the AI to access distant, relevant information almost instantly, much like a search engine can pinpoint a single relevant web page out of billions in milliseconds. The magic happens when native sparse attention and the Lightning Indexer work in tandem. The sparse attention reduces the sheer number of calculations, moving away from that costly quadratic scaling. The Lightning Indexer then ensures that the remaining essential calculations are performed with unparalleled efficiency. Together, they create an architecture that radically redefines the cost structure of large AI context windows. Instead of spending $5 to process 1 million tokens, DeepSeek V4 Flash leverages these two innovations to bring that cost down to a remarkable 14 cents. This isn't achieved by making the model dumber or less capable. DeepSeek Flash still offers strong performance on coding tasks, often competing with or surpassing models that cost significantly more per token. The dramatic cost reduction comes from fundamental engineering ingenuity, rethinking how AI processes information at scale. A price point of 14 cents for a 1 million token context window opens up entirely new possibilities for AI development. For individual developers and small startups, it makes ambitious, context-heavy applications financially viable. Imagine an AI agent that can ingest entire legal codes, hundreds of thousands of lines of legacy software, or years of company documentation, and then reason over it all in real time for mere pennies. This is no longer a luxury reserved for well-funded research labs. It's becoming an accessible tool. The sheer absurdity of the scale is what makes it so beautiful. Processing data that would take a human days or weeks to read, considering 1 million pieces of information, and doing it faster than you can blink for less than the price of a gumball. It's a testament to the continuous innovation driving AI, pushing boundaries not just in capability, but in fundamental economic efficiency. This incredible reduction in cost, driven by clever architectural design, is a crucial step towards making advanced AI ubiquitous. It shows that the future of artificial intelligence isn't just about bigger models, but smarter, more efficient ones, pushing the frontier of what's possible within our digital systems. For example, major pharmaceutical companies like Moderna can now continuously ingest every new peer-reviewed study, clinical trial report, and patent filing for a target disease, potentially hundreds of millions of tokens daily, to synthesize comprehensive insights for just a few $100s a day, a fraction of prior costs. This means a single AI can now effectively read and comprehend a new scientific journal every second, costing less than your morning coffee. Subscribe to Loopback, and the next video is waiting for you on screen right now.